In this video, you'll learn how Newton's second law explains the relationship between force, mass, and acceleration. Through simple diagrams and real-world examples, we'll explore how forces affect motion and why this law is fundamental in both physics and engineering. When a single force is applied to a block, it accelerates in the direction of the force. This illustrates Newton's second law, F equals ma. When the same force is applied to two blocks of different masses, the smaller mass accelerates more. Acceleration is inversely proportional to mass. When two opposing forces act on an object, like a push and friction, the net force determines the direction and magnitude of acceleration. At rest, an object on a table experiences balanced forces. The normal force balances the weight, so there is no net force and no acceleration. On a frictionless surface, an applied force to the right causes unbalanced motion, while vertical forces remain balanced. On an incline, the object's weight is resolved into two components, one perpendicular and one parallel to the slope. Only the parallel component contributes to acceleration down the slope. In everyday life, pushing a cart involves applying a force. If the cart moves, that means a net force is present and it accelerates. In a rocket launch, thrust pushes up against gravity. If thrust is greater than weight, the rocket accelerates upward. A parachutist descends steadily when air resistance balances the gravitational pull. This is an example of zero net force during motion. A common misconception is that constant force means constant speed. In reality, a constant force causes a continuous increase in speed. That is, constant acceleration. An object like a puck gliding on ice moves at constant velocity when no net force acts on it. This illustrates Newton's first law, reinforcing the idea that net force is needed to change motion.